So we defined this dual graph, right? So the definition of dual, let us recall. So the thing is, suppose you have a planar graph G, then what you do is, so face of a graph, or you can replace, so the vertices corresponding to the face of the graph G, and the edges of the dual graph will correspond to the as follows. For example, if E is an edge of G with face X on one side and face Y on the other side, then there will be an edge between the E star is an edge in the dual graph where the endpoints are the face X and face Y. So for example, here this is a face and this is a face. So this will be an edge that in the dual graph that is corresponding to this edge E, right?
Yeah.
Okay, so the definition is fine. Okay, so next one of there is some echo. One example is, so two embeddings of a planar graph. So may have non-isomorphic duals. So it means that suppose I can have a embedding, planar embedding I can have in many ways, right? So that can be non-isomorphism. Okay. So each embedding,
I suppose.
right? So we can have. So let us draw and see an example. What is happening? So each embedding shown below has three faces. So this will imply the dual graph has three vertices, right? Right, let us see the graph or the embedding. So this is a planar graph, right?
Yeah.
So this is a planar graph, and what are the faces? So this is one face, this is one face,
True.
and this outside is the one face, right? These are
True.
the three faces. So I can draw the same graph in a different way. So I can draw like this. These are the four vertices, and I draw them inside. Okay. So I can draw like this, right? So now also I have three faces. So this is one face, this is one face, and this is one face, right? So these are the same embedding or same graph, but two different planar embedding, right? This is two
But
different.
to emit in is isomorphic or not?
Yes, yes, these two graphs are isomorphic. So these two are graph are actually the same graph, right? So these two are, but the thing is, these are two different embeddings of the planar graph. So I'm two different drawing, right? Actually, of the same graph. So in the now we'll try to find the dual of this graph and see that they are not isomorphic. So that is what they are saying, right? So it can have that same planar graph has two embedding, but the duals may be non-isomorphic. So let us see the duals. So first of all, this there will be an edge like this, right? because this is an edge, right? Now, because of this edge, there will be an edge like this. Now, because of this edge, there will be an edge like this, right? Okay. So now next is this. This will be like this. Okay. Because of this edge, there will be a loop. Okay. Now next one is because of this edge, there will be like this, and because of this edge, there will be like this, right? One more thing is left is this one. So this one is in the outside thing, so there will be a loop, right? So you loop, right? So if I draw it a clearer way, then it will be. So there are three vertices. So we have to see actually that they are not isomorphic, right? So let us name the vertices. So this is suppose 1, 2, and 3. Right. So there is a loop in 2 and a loop in 3. So 2 there is a loop and 3 there is a loop. So 1 and 2 there is only one edge. Then between then between 1 and 3, how many edges are there? There are two edges, right? So between 1 and 3 there are two edges. Between 2 and 3, how many edges? 1, 2, 3 edges, right? Okay, fine.
Yeah.
So this is my graph. So this is the graph. Then let us see what is happening to the other graph, the dual of the other graph. So I think all of the edges are covered, right? Just to verify. So 1, 2. Okay, so degree of 1 is 3. Degree of 1 is 3. Fine. Degree of 2 is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. 3 is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Yes. So all of them are covered. Now let us see the dual of this one. Okay. So this has connection with this because of this edge. This has connection with this, right? Now this is inside this one. So this is a loop. Now this one is again a loop, right? Now for the outside part, this will be 1, this will be 1, then from here this will be 1, and the above one, right? So above one go like this, right? So let us see what is happening. So this is 1, suppose this is 2, and this is 3. So if I draw it here, so 1, 2, and 3. So now here you can see the both of the loops are in 2, right? So this is one loop, this is another loop. So then what else? Between 1 and 2, two edges, right? So between 1 and 2 there are two edges. Now between 1 and 3 there is one edge, right? And between 2 and 3, how many edges? 2 and 3 is 3 edges, right? Right. So these are the dual of the same graph, but it is embedding is different. But these two duals are automatically, you can see that they are non-isomorphic because the single vertex has two loop, but here there are two vertices with a single loop. So these two graphs are not isomorphic. So we found an example. Yes.
But it's not the statement, is right?
Yes, this is a statement, right?
Non isomorphic. Okay.
Non-isomorphic duals, right?
Non.
Right. So, so this is the observation. So next, what we have is Okay, so we'll see maybe. Okay, let us see one definition. So this is an observation. This will maybe will prove later. So every every three connected planar graph, it is has essentially one embedding.
Mm.
It's, so the thing is, so in case of three connected planar graph, so it has essentially one embedding. So in that case, the dual will be unique, right? So that is not a problem. So we'll see the proof later. So this is one observation. And when a plane graph is connected,
Mm.
the boundary of each face is a closed walk, right?
Mm.
Is a closed walk. And so for what does it mean? So for example, so this is a face, right? So
Mm.
this is a face. Then if I see the boundary, so this one is a boundary, right? So boundary of the face. So this is a closed walk, right?
Mm.
Or we can use this edge also. If we walk, we can repeat, right? So this one is also a closed walk, right? So that is what is saying. And when the graph is not connected,
Mm.
when the graph is not connected, there are faces whose boundary consists of more than one closed walk. Right. So suppose the plane graph is disconnected. So suppose I have simple two disconnected graphs. So I take a triangle and take a square or a
Mm.
cycle. So then these are suppose this whole thing is a single graph. So this is disconnected and it is planar. So now if I consider the outer face, this outer face has the boundary is two closed walk, right? So it has the boundary consists of more than one closed walk.
More than one cloud.
Closed walk.
Wow.
Right?
Mm. What does it mean, cloud?
Closed walk is the walk is closed, right? The starting point and the end point is same. This is a closed walk, right?
Ah,
Yes, more than one closed walk.
more than one cloud. Ah, ah.
So when it is connected, we saw that the boundary of each face is a single closed walk, right? So for example, this we saw here, right? In this case, suppose I consider this face, or if I consider this face, then the boundary is a triangle. So this is a closed walk, right?
Mm. Mm.
Right. So similarly, but if the graph is disconnected, then the boundary there are faces whose boundary has more than one closed walk.
Mm.
Okay.
Mm. Yeah.
Right. So the next definition is based on this one. So the length of a face in a plane graph G is the total length of the closed walk in G bounding the face. right? So the length of a face in a plane graph will be the total length of the closed arcs that is bounding the face. So that is the definition. Right. So an observation. So a cartridge belongs to the boundary of only one face, right? So it will belong to the boundary of only one face because both side of the cartridge is actually in the same face, right? And it contributes twice to its length because the cartridge will be covered twice when you have a closed walk, right? Okay,
Yeah.
right. So now let us. Based on this, we have the next proposition. So if L of a phi, so this denotes the length of the face a phi in a plane graph G, then twice the number of edges in G is actually the summation of length of a phi, right? Yeah, twice the number of edges is actually the sum of all length of all face a phi. Okay. So this is similar to that degree sequence, right? That relation between the number of edges and number of then the summation of the degree, right? So let us see the proof. The statement is fine, right?
Yeah, yeah.
Right. The face lengths, the face lengths are the degree of the dual graph, right? The degree of the dual vertices, right? So the number of so here if you see the example, so okay. So the thing is, so degree of the vertex. So this is the dual vertex, right? This two is a dual vertex. So what is the degree? The degree is how many faces, how many edges it has, right? So the closed walk, if we see the boundary of the face two, then what is the boundary? This is 1, 2, 3. 3 is coming back. 4, 5, 6. The total length is 6, right? So the length of the face, that is the boundary of the two, will be nothing but the degree of the vertex 2 in the dual graph, right? So that is what it is saying. The face length are the degree of the dual vertices. And since the number of edges in G and number of edges in G star are same, G star is the dual graph. So we have uh, the number of edges in G is equal to the number of edges in G star. So that is nothing but summation of length of Fi because length is the degree of the. So we can write one more step. So this is degree of G star X summation over all vertices, but that is nothing but degree of the vertex X is nothing but the length. So the summation over all 2i is the number of edges. So this is the 2i's. 2i is the number of edges is nothing but the summation of length of all edges faces, right?
Yeah.
Okay. So next, the natural question asks is what about the coloring? So coloring of dual graph, can we say something, right? So we can also interpret uh, coloring of coloring of G star in terms of G. The edges of G star represent a shared boundary between faces, right? Between the faces of G, right? Hence the chromatic number of G star, the dual graph, so that will be equal to the number of colors that is needed to properly color the faces of the graph, right? So if we can properly color the faces of the graph, then we are done, right? So the proper coloring of face means if the two faces are share a boundary, we give them different color. That is the proper coloring of a face, right? So now, since the dual of a dual, so if we take a dual of a dual of a connected plane graph, then we get back the original graph, right? So we get the original graph. So this means so four colors will be sufficient to properly color every planar map, right? So this means that four colors suffices to properly color the region in every planar map. If and only if every planar map has chromatic number at most 4, right? So up to this part is clear, right? Find it.
Yeah, yeah.
Okay. So the next theorem is based on this one. So it says that edges in a plane graph form a cycle form a cycle in G if and only if the corresponding dual edges form a bond in G star. G star is the dual graph.
is in graph from a cycle from a violin. Gista is in plane graph from a cycle.
Right.
Yeah, we can get some example.
Yes, example, but the definition of bond do you remember, right? So bond we defined I think long back. So bond
Uh,
is a minimal non-empty,
bond, not
right?
power rate, bond.
Yes, yes. Bond is we define to be the minimal non-empty cut, edge cut. So the a set of edges, an edge cut is a collection of edges, right? So for example, suppose we have, okay, let me think of an example. Right. So suppose we have this graph. Okay, let us just draw in a general sense. So suppose I have two things. So here there is a vertex and here there are two vertices, right? So suppose it is connected like this, right? Then if I delete these two edges, then the graph becomes disconnected, right?
Mm,
So then this two set of edges, that will call be an edge cut, right?
mm,
So the minimal non-empty edge cut, that is called a bond.
mm,
So the thing is, the corresponding dual edges, if they form a bond in G star, then we will say, have that the edges in a plane that form a cycle, right?
mm. Yeah, yeah.
Okay, so let us see the proof. So let us take a subset of the edge set. So consider. Then suppose we first assume that D is a edge set of a cycle in G, right? Edge set of a cycle in G. So we'll see that the corresponding edge set D star is actually a, in the dual graph is a bond that we have to show.
Mm,
So the corresponding edge set, that is let us name in D star, that is corresponding to is a subset of the dual graph,
mm,
contains all dual edges joining faces inside D to faces outside D. So hence, so this will imply that D star is nothing but a edge cut. So it contains an edge cut. So let us see an example, and then we will understand. So if we say take the same example, what we draw in this one, let us copy the example. Right. So here, first let us take an edge that is a set of a cycle, a edge set of a cycle. So for example, here is a cycle. So if I consider those edges, so let us name the edges. That will be clear. So so this is so this edge is suppose E1, E2, E3, and E4. So these four edges I am taking. So D is my set E4, right? Then the corresponding edges in the dual graph. So for E1, the corresponding edge is this one, E1 star, right? For E2, this edge is E2 star. Then for E3, this is E3 star, and this is E4 star. These are the corresponding edges in the dual graph, right? So now let us mark the edges here. So E1 star is between 2 and 3, right? So let us take suppose E1 star. Then between 2 and 3, right? E3 star is also between 2 and 3. So this is suppose 3 star. And E2 star is also between 2 and 3. So this is E2 star. And E4 star is between 2 and 1, right? E4 star, right? So the D star, the corresponding edges in the dual graph. So this is E1 star, E2 star, E3 star, and E4 star. So now one can check that if I delete all these four vertices. So if I delete all these four vertices, then the graph becomes disconnected, right? Right. So if I delete all these four vertices, then the graph becomes disconnected. So your this is one part and this is one part, right? So this is actually a cartridge, right? So this is a cartridge. So that is what we wanted to show, right? That if we take the dual graph and if we take only a set of that is a cycle, that is the set of edges that form a cycle, then the corresponding in the dual graph, those edges will be a cartridge. Okay,
Yeah, this is okay.
right. So now we have to prove the converse part. Converse part is we
But
assume that
but
yes,
but it's not minimum is right. A bond in the minimum.
yes, bond is a minimum. Yes. So this is minimum. Minimum, yes, minimum we have not proved. So this
Mm,
is I have only showed that it contains a cartridge, right? So
okay.
the thing is here actually you can see. So these two, the boundary is actually not length 4. The length is 6 because this edge also come, right? But I have not taken into consideration of this edge, right? So I have taken only the edges on the cycle, right? So that's why it will give minimum. Yes, the minimum will come.
But we have two cycle here.
2 cycle means
The triangle more
yes,
cycle.
yes. Any cycle we can take. So for
So one of them is a bond, not
yes,
bow is right.
yes, yes. So the for the if I take the triangle, then 3 edges will be sufficient. So that's why minimum will come. So that will depend upon the size of the cycle. So for example, if we consider this triangle, the corresponding edges will be these 3 edges. So if I delete these 3 edges also, then also the graph becomes disconnected.
Hmm? Yeah, yeah.
Right?
Mm.
Right.
Yeah, yeah.
Okay. So let us continue with the book. The example I think it is fine. So now, so if the original set D, that is the contains a cycle and more. So it has some more edges than a cycle. Then D star contains an edge cut and more. It will also have an edge cut and some few more edges, right? Then and if D contains no cycle in G, then it encloses no region. It remains possible to reach the unbounded face of G from every other without crossing. So hence, if we delete the D star, so hence G star minus D star, so that will remain connected. This implies that D star does not have a cut edge. So this implies that minimum we have to cover a cycle inside the D. So thus D star is a minimal cut edge if and only if D is a cycle. So if we have something less than a cycle, then the corresponding is not a cut edge in the dual graph. And on the other hand, if I have cycle with few more edges, then we'll have some extra edges than an edge cut in the corresponding cycle. So hence the minimal will come from when we have taken exactly the edges of a cycle. Fine.
Okay.
So next one is one remark based on this theorem. So if we delete a non-cut edge of the G, so deleting a non-cut edge. So cut edge is that a single edge that when we delete it becomes disconnected, right? Of G has effect of contracting an edge of in G star. As two faces of G merge into one. So let us see an example what they are saying. So suppose I have this graph. So this is a graph on 4 vertices. This is a planar graph, that is fine. And now this edge, this middle edge, it is not a cut edge, right? It is not a cut edge, right? So the corresponding the now the dual graph is, so here is one face, here is one face, and here is outside there is one face, right? The corresponding dual graph will be, this will be the edge, this is edge, this is one edge, right? So this is one, and outside this is one, right? This is a graph, dual graph, right? Now suppose if I delete the edge in between. So suppose I delete this cartridge. So this is my new graph. So I have deleted the cartridge. So then there is only one face in the between, right? So previously there were two faces, but now there is only one face. This one is face inside and one outer face, right? And the corresponding, this will be your dual graph, right? So what does it happens? So it happens that these two faces, actually these two faces actually merged into a single face. So in the corresponding in the dual graph, these two vertices get merged into a single vertex. So that is their saying, right?
Yeah, yeah.
Okay,
It's okay.
right. Now if we contract it, the next observation is contracting a non-loop edge of G has the effect of deleting an edge in G star. Right. So what does it say? So suppose if we contract a non-loop edge in G, then the correspondingly in G star we'll also delete an edge. So let us take the same example. So this one is same. So now suppose what you're doing is we are contracting an edge, right? So contracting a non-loop. So this is edge. This okay, let us do. So this edge let us contract. So let us contract means this will become a single vertex, right? So these two things will merge. So the corresponding graph will look like this one. So if the edge E is contracted, then we have this thing. This is my new graph, right? So E is contracted, right? So then what will be the dual graph? So dual graph has still three faces. This is one face, this is one face, and this is one face, right? But now see that okay, let me write. So this is one outside, and this is one. So here you can see that these two faces are not sharing any edge, right? So that's why there will be no edge between them. So this edge got deleted in the G star. Okay, that is what they're saying. Fine.
Yeah, yeah.
Okay. So next one is, so to keep the duality dual graph, to maintain the dual graph. So note that maintain this duality. So we keep multiple edges and loops that arise from edge contraction in the plane graph. Okay.
Mm.
So up to this is fine, right?
Yeah, yeah.
Okay. So this gives us the next theorem. So the following are equivalent for the plane graph G. The first point is G is bipartite. The second condition is every face of G has a eval length. And C is the dual graph is Eulerian. So these three conditions are actually equivalent.
Mm.
So this implication is easy that A implies B. So let us see that.
Mm. Mm. Bipartite. Mm.
So in a bipartite graph, we know that there is no odd cycle, right?
Mm.
So if I want to prove A implies B, so if a face of a face boundary consists of closed walk, right?
Mm.
Now every odd closed walk contains an odd cycle, right?
Mm.
Other than that, we cannot have a odd closed walk, right? It should have a odd cycle, right?
Mm.
But the thing is, bipartite graph cannot have a odd cycle, right? By definition, bipartite graphs do not have odd cycle, right?
Mm.
So this implies, in a bipartite plane graph, the contribution to the length of a face is always even, right?
Mm. Mm.
So this implies that every face of G will have an eval length, right?
Yeah.
Right. So this proves A implies B. Okay. So B implies A, and then we have to prove that B and C are equivalent. So that will take some time. Maybe tomorrow we'll continue. Okay.
Mm. Yeah, yeah.